this video, I'm going to give a brief introduction or review, really, of the fundamental aspects of quantum mechanical spin, which we can think of as an intrinsic angular momentum. Okay. So all fundamental particles have some intrinsic angular momentum, which we refer to as spin. I guess I shouldn't say all because the Higgs boson has spin 0, but all the other fundamental particles have some non-zero intrinsic angular momentum, which again, we refer to as spin. Now, so a very important thing that one needs to know about spin is this is not a result of the particles actually spinning in the classical sense. Now, at first, scientists thought maybe that's what was going on, but it turns out that does not match with reality. Sometimes it's helpful still to picture, say, an electron which has some spin spinning there in space, like the Earth is spinning. Sometimes that's helpful, but it's very important to remember that that's not actually what is going on. So we should not think about an electron as being a little ball, which is spinning, causing it to have this intrinsic angular momentum. It's actually quite different from that. And it's a feature of quantum physics that there just simply isn't a classical analog that we have to help you understand and have some better picture. So one of the reasons the spin is really different from classical angular momentum is that its value cannot be changed. So all of the fundamental particles are going to have a given spin amount. So for instance, the spin of the electron is 1/2 times h bar, 1/2 times Planck's constant. And this value can't be changed. The only thing you can change is the direction of the spin. A spin is going to be quantized, and therefore it's conventional to discuss spin as a fraction of Planck's constant, which is h bar, right? So fermions, all of the fermions that we know of in nature, we'll see are going to have spin 1/2, which really means h bar over 2. When we say spin 1/2, we really mean a half of h bar. And all bosons are going to have integer spin. And the only bosons that we understand under the framework of the standard model of particle physics are going to be the Higgs boson, which actually has 0 spin. And then all of the force-carrying bosons, like the photon, they're going to have spin 1. If one day we discover a particle known as the graviton, that would have spin 2, which again really means 2 times Planck's constant. So it's important to remember that when people talk about the spin of these particles, they're always talking about some fraction of Planck's constant. And again, that value can't be changed. So it's better to maybe think about spin as something like charge, right? An electron has some set charge. That's that property of the electron. I'm talking about electric charge, right, of the electron. And you can't change it. So similarly, electron is going to have spin h bar over 2, or like often we say spin 1/2, and that value can't be changed. So in this way, it's really an intrinsic property of the electron.